We're going to continue on here, chapter 10 we're on, and chapter 10 is about energy we started talking about. And remember when we talk about energy, we talk about heat, and heat does flow, as we talked about, from hot to cold. And when we're talking about sort of energy and sort of thermodynamics, again, we're talking about the system and the surroundings. And as we talked about, we were really talking about the kind of the flow of energy, kind of from one to the other. And there's sort of that law of conservation of energy, like we talked about, which is again, energy is not created nor destroyed, but it can transform from one form to the next. And we kind of think of it, as we talked about, sort of as a perfect sort of transfer of energy, which means, again, if somebody loses a certain amount of energy, somebody else will gain pretty much the same amount of energy. Really, in terms of values and stuff like that, the only difference that we kind of see is in the sign of it, depending on what type of process is occurring. And we talked about two types of processes, and we'll talk more about it today as well. We have exothermic type of process, and an exothermic type process, that's when heat and energy is released. The opposite of that is really an endothermic process, and in an endothermic process, heat and energy is absorbed. So we talked a little bit about the idea of, for example, phase changes, and as you go from solid to liquid to gas, those are all processes where energy has to be absorbed by the system. So if we think about like water or ice to start with, if you take an ice cube out, it'll gain all the heat and energy from the surrounding air, causing it to melt. If you take liquid water, it will continue to pretty much absorb energy if you start to heat it, say, as you're going to boil some water, and that will turn that liquid water into steam, which is the gas version. So as you go from solid liquid to gas, those are all processes where energy is going to be kind of put in. Opposite is true if you're starting sort of in the gas phase. So if you have, say, like some steam moving around and you cool it down, it will go to liquid water. If you continuously cool down the liquid water, which is essentially removing the energy, that is going to go into the solid phase. So what happens as you remove that energy is everybody will basically come together, as they don't have enough energy basically to escape one another. The terms of sign of these things, exothermic is negative, and when we'll see in this chapter as we go through it, positive value there for our endothermic type processes here. Any questions on any of that stuff there we talked about last time? We also talked about some other types of energy. Thank you very much. We talked about, for example, energy is stored within bonds as well, in sort of molecules. So as you break bonds, that is also an endothermic process. Energy has to come in to break those bonds. And when you're trying to actually make bonds, as we talked about, that is an exothermic process. So energy has to be released, allows again for them to kind of slow down and come together to bond. So continuing on here with our topic of heat and energy, as we just talked about, there are different types of processes there. Again, heat flowing from hot to cold, and it will always transfer that energy because of really the difference in temperature between those two things. Remember, as well, as we also talked about some important units of energy, that is joules or kilojoules, and those are really probably very common units that we'll see the most probably in here. There's also calories and kilocalories, also very common sort of unit of energy. And remember that 1 calorie is 4.184 joules. That is definitely a conversion you should know, as we talked about last time. And as we also talked about, I think at the very end, and we'll see it again, I think today as well, that is also a number that's known as the specific heat capacity of water. So that 4.184 number does pop up a lot, especially in these type of calculations. So again, exothermic process going to release that energy. Lighting a Bunsen burner or a match, you could feel, you know, if you kind of put your hand near it, you could feel the heat and energy coming off of it. And obviously that is going to be an exothermic. And again, endothermic, anything that absorbs energy, like our ice cube example. Also, we might have talked about last time, again, like, you know, kind of those hand warmers or coolers. You do break a reaction or something in the little pad. And again, if it's going to sort of warm your hands, it will give off energy and your hands are going to absorb all that energy. And that is how you start to feel warm when you're holding those things. Opposite is true if you want to have something that'll cool it down is you do a reaction and it's an endothermic reaction, which means it will suck out all the heat and energy from your hands and again, make your hands feel colder. And that's sort of the same idea if you're holding a test tube, for example, in a chemical reaction. That test tube starts to heat up. That's an example of that reaction in the test tube's exothermic. It's releasing all that heat and energy into your hands, and obviously you can feel it. And same thing if you're actually holding a test tube and it was an endothermic reaction, you would actually feel it start to get colder again because it's kind of sucking out the heat and energy from your hand into the test tube. And again, that's why you kind of feel something hot or cold in that particular case. So these are energy diagrams, and let's talk a little bit about the different sort of ways that these energy diagrams sort of look. These energy diagrams do represent the two types of reactions we've been talking about, which is an exothermic reaction or an endothermic reaction. And on the left-hand side there, we have an energy diagram for an exothermic reaction, and on the right-hand side, we have it for an endothermic reaction. When we do have a reaction, as we talked about a little bit, and again, they kind of assume that you've done reactions since we kind of skipped ahead a little bit. But when we have a reaction, we have our reactants on the left-hand side of the arrow that go to our products on the right-hand side of the arrow. And again, the reactants are really our starting material. So that is whatever we're kind of starting with in the reaction. The products are pretty much what is formed as a result of that chemical reaction. Again, this is sort of our initial stage, the reactants, and our products are kind of like our final stage. And when we look at this energy diagram here for our exothermic reaction, right here's our reactants, and down here is where our products end up in terms of energy. And in this situation, whenever we see in sort of an energy diagram that our reactants are basically starting higher in energy than our products, the end result of that is energy has to be released in this case in order for those reactants basically to get down to the products there in terms of their energy. So overall energy has to be released, which is why this guy on the left here is an exothermic reaction. When we see what happens in a reaction is pretty much this. The reactants will start out and they will start to, for example, rise in energy here. And as they rise in energy, they will eventually come up this hill to really the peak sort of spot there in terms of energy. And really when a chemical reaction takes place, there's kind of two things that has to happen. You have to have collisions, so you have to have things basically hit each other. And they don't only have to hit each other, they actually have to hit each other in the right location. So they actually have to hit each other in the right sort of active site with those two molecules to allow a reaction to take place. And they also have to hit each other with the right amount of energy to allow basically a reaction to occur. So sometimes people think all of that has to happen. It's like two things just got to come together to make products, say, in a chemical reaction. And that's not necessarily true. There are sort of collisions that occur between molecules that do not result in products being formed. They have to hit each other in the right location. They have to hit each other with the right amount of energy. And that right amount of energy is really the difference in energy between where the reactants start and that kind of top of the hill there. And that is what is referred to as the activation energy. The activation energy is sometimes abbreviated E of A. And that is basically the minimum amount of energy needed for a chemical reaction to occur. So this activation energy, if you want to think about it, is basically the hill that those reactants have to sort of climb to get down to the other side. Now, when we get to the very top of this hill, which is pretty much in this picture where I have that kind of circle, we'll make it blue now, right there, this is what is sometimes referred to as the transition state. And the transition state is pretty much in a chemical reaction the highest point in terms of energy. And one thing that you should know in terms of energy and sort of chemistry in general is things that are in high energy is not really a stable situation. It's not really what things want to be in. Things typically want to be in the lowest possible state of energy. So at this point, it's in pretty much the highest possible state of energy, which makes it not very stable. And usually what will happen is these guys will kind of fall down pretty quick down the hill to the other side to make products. At the very top, where the transition state is, you sometimes have what is referred to as the transition state complex, or sometimes referred to as the activated complex. And what that is actually a sort of compound that has partially broken bonds and also partially made bonds. So in a chemical reaction, the only thing that happens in a chemical reaction is we pretty much break all the bonds that we have on the reactant side, and then we make new bonds on the product side. So it's all about breaking bonds and making bonds when we have a chemical reaction. So in this case, we're going to break all of our bonds on the reactant side and make new bonds on the product side to make our new products. So as this thing is really sort of progressing up the hill, the reactants, you're starting to get things that are partially breaking some bonds. And at the same point, they're actually making some bonds as well. So you got these partially broken bonds, you got some bonds being partially made as it works its way up this big hill to get to the top. So when you get to the top and you hit this transition state complex, you have really this intermediate, as I mentioned, that has these kind of partially broken bonds, not fully broken, partially made bonds, not fully made, a really sort of intermediate. And this is why it's really the highest point in energy. It's really like a transition part sort of guy there to get us to our products. Transition state complexes don't hang around a really long time because they are so high in energy. They typically will drop down to the other side relatively quickly. And again, that is classic what we see here in an exothermic reaction, this big hill to get to the other side. Now, one of the ways, as we'll talk about here in this chapter, to think about energy and reaction, we might have talked about last time, is what is referred to as the delta H. And the delta H is the change in enthalpy. And the change in enthalpy is, again, a fancy way of basically just describing really the heat of a reaction. Is energy overall being given off in this reaction? Is energy being absorbed in this reaction? And that's really what the delta H sort of represents. One way, as we'll talk about here in a second, that we could calculate the delta H for a reaction is to basically take the delta H of all of our products minus the delta H of all of our reactants. And that's basically our final state minus our initial state when we do that. So if we just look at, for example, our exothermic reaction here, here's the energy of where our reactants are. And this is basically the energy of where our products are. And if we take sort of the difference there in those energies, the delta H is what we would be calculating. So just looking at the picture, we could see that if we were going to take the delta H of our reaction, which is equal to our delta H of our products minus the delta H of our reactants, when we look at their products, that is a smaller number minus a larger number in terms of energy because it's way up here. So when we take a large number minus a small number, we actually end up with a negative value. So that's how we know when we see a delta H value that is negative, it is an exothermic reaction, and the only way to get that is our final state in terms of energy. It's actually a lot less than our initial state, and that will usually end up giving us a negative number for our energy value. And that again is sort of very hallmark of a exothermic reaction. Any questions on that? Yeah. Yeah, delta H is the name of it is the change in enthalpy. That's what the little delta symbol means. The little triangle in front of it. That's the delta symbol, and that's the change in enthalpy. It is really describes basically for a reaction overall. What is happening in terms of energy is overall going to be sort of an exothermic reaction, which means this guy's going to release energy overall, or it's going to be an endothermic reaction where overall it's going to kind of absorb energy. So that's basically kind of what it tells us. Yeah. Other questions? Now, if we look on the right-hand side here, this is also an energy diagram, and it does look a little bit different. It is a endothermic reaction, and really the way you can really tell the difference here is the location of our reactants versus our products. So when we look at our reactants here, it's way down here where our reactants are starting, and our products are actually way up here. So the only way for those reactants to get up to the products is energy actually has to be absorbed. Again, the same idea here. It's going to climb this hill, start breaking bonds, making bonds until it gets up to the very top, which once again is our activation energy, the difference between here and the top of the hill. That is our activation energy in this particular one. You will again have the transition state at the very top of the hill there, and our transition state complex, which will come back down the hill relatively quickly. Now, when we look at this, though, in terms of our delta H for this reaction, we're again going to take the difference in energy of our reactants and our products here. And we'll do our difference here is our delta H. And once again, if we just look location-wise of where our products are to our reactants, in this case, our products are actually higher in energy than our reactants. That means in terms of number, our products would be a larger number minus a smaller number. And that's going to yield you typically a positive value for delta H. And that tells you that it's an endothermic reaction when you see a delta H that's going to be positive. Again, that's the only way you can do that. It has to absorb that energy overall. That reaction is picking up energy to give you that sort of difference in terms of where our reactants and products are located. So these energy diagrams, if you see one, whenever you got reactants higher in energy than products, always going to result in an exothermic type reaction. And when you have reactants that are actually lower in energy than products, then it's going to be an endothermic reaction. You could also see quite a difference when you look at the hill that is there. This is our activation energy hill. And over here is our activation energy hill. And you can see in the endothermic one, we do have a larger hill to sort of climb to get to the other side. Also makes sense that, again, you maybe this little endothermic needs to pick up some energy to get people up and over that hill for this reaction to take place. By the way, the activation energy also plays a really big role in how fast or slow a reaction takes place. So if you have a tremendously big activation energy, you're not going to have as many molecules. They'll have enough energy to basically get up and over to the other side. So the result of that is it will also take some a lot longer to get enough energy to get up and over to the other side. So it also will usually slow down a reaction. Wouldn't be as fast as if you had a very small hill to climb. So for example, if you're in the parking lot and just a little speed bump, you could get up and over that hill pretty quickly, right? If you had to walk up, from here all the way up to the other side of the campus, up a big hill, it's going to take a lot longer, right, to get up and over to the other side. And again, same idea here. So that activation energy is really sort of an energy bearer hill that plays a role in how fast or slow a reaction can take place. One of the ways we'll talk about in a later chapter that you can speed up a chemical reaction is you could actually add a catalyst. So one way you could actually speed this up is to add a catalyst to a reaction. And a catalyst is actually not a reactant, nor is it a product. It actually does not get used up in the chemical reaction. Really, the only sort of function of a catalyst in most cases is to speed up a reaction. And the way it does that is it kind of finds an alternative pathway, a more efficient pathway for that reaction to take place. So for example, if we had gas molecules flying around by themselves, it may take a while for them to kind of find each other and react. Now, if you add a catalyst, which sometimes is just a metal, for example, and maybe you have this metal that you add, then maybe these gas molecules are attracted to the metal, and now they're going to be in a very close proximity to each other and going to allow them to react a lot faster than if they weren't attracted to that central location. They got to go fly around and kind of find each other. So a lot of times catalysts, again, not a reactant, not a product. By the way, catalysts are oftentimes written right there on top of the arrow in a chemical reaction. It may just say, for example, something like PT, like platinum is a metal catalyst that's used, or something like that. Or it may say H plus, like an acid catalyst is used. But they're usually written right there on top of the arrow when you look at a chemical reaction, if there is one sort of listed. What the catalyst actually is able to do, because it's able to find this kind of more efficient way for this reaction to take place, what it does to the energy diagram is it actually will lower, for example, lower the activation energy. Bless you. So in a catalyst type reaction, it will result in a lower activation energy. And that's really important because with that lower hill to climb to get to the other side, you're now going to have a lot more reactants that have enough energy to actually get up and over the reaction a lot easier. And that's going to cause the reaction to take place a lot more times because those guys can get up and over that smaller hill a lot easier. Any questions on that there? And here's just another sort of version of an energy diagram. These are reactants, again, higher in energy than our products. The result of that is heat's going to be given off. So exothermic delta H value here would definitely be a negative. Down here, this is actually our reactants going to our products in this case. And again, our reactants are lower in energy than our products. So energy, as you can see here, has to be kind of put into this reaction. Again, going to give us an endothermic process where we will end up with a delta H that's going to be positive in this particular case. Any questions on that there? Now, we talked a little bit, obviously, about the sign of exothermic and endothermic and what's happening. Another couple of ways that you sometimes will see exothermic and endothermic displayed is actually in the chemical reaction. So not a lot in our class, but occasionally you may see it, actually a energy value put in to a chemical reaction. And for example here, this is an energy value, 213 kilocalories. And where we see it actually located is on the product side. And if you actually see a chemical reaction where they put an energy value into it and it's on the product side, that is like it's being given off because that's supposed to be in form. So it's like energy part of the products and it's being given off. And that will tell you it's a exothermic reaction. And sometimes we do consider energy, and it's not really correct in all aspects, but we do consider energy as a product when we're dealing with a exothermic type reaction or process. Yes. There usually will always be some sort of heat or energy transfer somewhere in a chemical reaction in some case. So either it'll be absorbed or are basically released. So either the reaction will pick up a little bit from the outside or it will release some to the outside. So there's be one or the other sort of happening, usually as a result of a chemical reaction. Other questions? Okay. Now, in a endothermic reaction, it's sort of opposite. Here's an energy sort of value, and it's actually a reactant. And in a reactant, basically, energy is being absorbed. So we think of it, or sorry, we think of in an endothermic process that energy is a reactant because it's being absorbed or being added in. So we think of energy in an endothermic process as being a reactant. I will say most cases you will probably not necessarily see the stuff written into the equation, but you'll see like a delta H value given to you in most cases. And once again, as I mentioned last time, when you're given a delta H value sort of in this context of is it exothermic or endothermic, the number really doesn't matter. It's actually the sign that's really important. So if you see a negative delta H, whatever the number may be, you know it's going to be exothermic. And same thing here, you usually will not kind of see it written in most cases, but you'll just see the reaction, and at the end, delta H is positive, some type of number. And again, it's that positive value that really kind of tells you it's exothermic or endothermic. So very rarely, I would say, probably through your chemistry career here, you would probably see the actual values written in the equation. More often, that is more how you'll see it. You'll see the chemical equation next to it, some type of delta H value given to you, and either positive or negative will essentially indicate if it's exothermic or endothermic. Any questions on that there? But again, if you want to think of it, and again, towards the end of this semester, when we talk about Le Chatelier's principle, when we have an exothermic or endothermic process, we think of either it being energy being a product in an exothermic sort of situation or a reactant in an endothermic situation. Again, as we talked about, sort of the flow of heat and energy, and again, it's going to flow from hot to cold in this case. Again, the hot water has a lot more energy than the cold water, and it's going to transfer that energy as it's banging around from the hotter side to the cooler side. And what will happen in that situation, and maybe it's in an ice insulated sort of container, is the temperature will kind of maybe meet halfway in the middle there. So if you took 90 and 10 is 100 divided by 2 is 50. So it'll meet somewhere in that middle, and they'll come to really equilibrium, um, which is a process where basically there's not much change going on, or it's able to maintain where it's at is basically what we mean by that. So the amount of energy will sort of equilibrate at this point, and the temperature really will equilibrate at this point. Now, enthalpy, as we were just talking about, is probably the most common way that we look at energy in chemistry in terms of chemical reactions. We don't do a ton of it in this class, but definitely when you get to 1A, you'll do a lot more of it. It really is sort of the basis of the first law of thermodynamics, which is that conservation of heat and energy, or energy. The enthalpy is used to express basically, again, as I mentioned, is heat being absorbed overall in the reaction, or is it being released? And the change in enthalpy is basically the way that we calculate it. And really, the way that we calculate, as I mentioned there, is we basically take all the enthalpy values for our products and we basically subtract it from all the enthalpy values of our reactants. So where do you typically get these enthalpy values? Typically, they are table values. So in a table, you could look up the delta H value. Is usually called the delta H of formation, or delta H of F, F standing for formation. And you could look up these values in a table. If you ever use one of these tables, a couple of things are really important when you go to those tables to look up values, which is obviously you want to find what you're looking for and make sure it is what you're looking for. But you also want to make sure that you find the actual state is in. Is it a solid, a liquid, aqueous, whatever it may be. You want to make sure that you actually look up the value and get the right value for the state that's in. I would say very common mistake people make when they do this type of calculation, for example, water. Water could be obviously liquid water, it could be solid like ice, it could also be steam. And when you go to delta H table, there's 3 different values for water, one for solid, liquid, and gas. So you want to make sure you always kind of look it up, not only just the thing you're looking for, but also the correct state. What you basically do is add up all of the values you have on your product side, and you basically just subtract it for all the values you have on your reactant side, and it'll give you a number. And once again, number probably not super important for us here, but again, the sign of the number is important in terms of is it exothermic or endothermic. So for example, if we had a reaction like 2A plus 3B goes to 4C. And we look up in a table here, and obviously I'm just going to make up these values here for delta H's for A, B, and C. We just look it up in a table. And these are typically in kilojoules per mole is typically the units that you'll find in that table in terms of the values. We'll just say A is minus 125. We'll go 35 positive for that guy, and we'll go minus 62. Obviously just making up the numbers. When we go to do this calculation, we wanted to calculate, for example, the delta H for this reaction. And we want to know, hey, what is the delta H of this reaction? So what we would do is we want to take a couple things into account. When we see these coefficients in these balanced equations, these represent the moles of each of those things. Moles abbreviated MOL. And we do have to take those into account when we're doing the calculation because 2A basically means there's 2 of those. So we got to like take twice the amount of value that we see in the table. For 3B, there's 3 of them, so we have to take 3 times the value that we see in the table. So if we were going to calculate this here, we would take the delta H of this reaction. We're now going to do all of our products, which is just this guy. So we're going to take 4, which is the coefficient, times the value that we find in the table for C, which is negative 62. And that would pretty much take care of all of our product side, basically. That's everybody we got on the product side, which again is our final state minus our initial state, which is our reactants. So we would then subtract it. And again, we're going to do the same thing on our reactant side. So we have a 2 for A, so we'll take 2 because of the coefficient, times the value that we find for A in the table, minus 125 kilojoules per mole. We then will add it to our other reactant in this case, since we have 2. And that also has a coefficient of 3. So we'll take 3 times the value that we find for B, which is 35 kilojoules per mole. On our product side, we didn't need to add anything because we only had one product. If we had multiple products, we would need to add, obviously, the values of those. So basically what we have here is all the delta H value is basically for our products where we end up, minus all the delta H values for our reactants where we started. And that's going to give us a number here. And we'll see how bad I did making up numbers. So we're going to take 4 times negative 62. We're then going to subtract it from 2 times negative 125. Again, the negative and positive values here are really important, so make sure you punch them in correctly. 3 times our 35. And that's going to give us a negative 103 kilojoules for our answer. By the way, the 4 and stuff like that are technically moles, which cancel out the moles that we see here, and that's how they kind of cancel out in that case. First off, any question on that calculation? So you basically just go to the table, find everything you need. You do have to multiply what you find in the table by the coefficient in the balanced equation, add up everything you got on the product side, subtract it from everything you got on the reactant side, and it will give you a number. This number right here should tell me this reaction I just made up is endothermic or exothermic. It is exothermic, this reaction. And it's exothermic simply because we got the negative sign, right? So overall in this reaction, we actually have energy being released. As a result of that, our products are actually going to be in lower energy than our reactants where we started with. Any questions on that there? All right, so why don't you try one here with a real equation, some real values you would find and see what you come up with. Calculate the delta H and determine is it exothermic or endothermic. Okay, so let's take a look at it. So again, we have a reaction here, and we would obviously go to a table to find these if you needed. And again, we're just going to take our products minus our reactants. So as we did in that kind of example a second ago, we're going to add up all the delta H of our products and subtract from all the delta H of our reactants. So starting on our product side, which is on the right-hand side of the arrow there, we have 2 sodium hydroxides, and there's the value. So our delta H of our reaction will be 2. Again, we do need to take the coefficient there into account, times minus 470 kilojoules per mole. We do have a second reactant here, which is H2. Coefficient is actually 1, and actually the value there is 0, and that's very common for things in their natural state by themselves. Uncombined, they're usually 0 values. So we'll take actually 1 times 0 kilojoules per mole. That basically takes care of all of our products here. We're then going to subtract it from our reactants, doing the same deal. On our reactant side, we have 2 times our sodium, which again is 0 because it's uncombined and by itself there. And we're going to add it to our other reactant, which is water in the liquid state. So we do have a 2 of them there in the equation, minus 286 kilojoules per mole. That will basically take care of all of our reactants basically on that side. So if we do all that good stuff there, we got 2 times minus 470 minus basically 2 times negative 286, maybe a negative 368 kilojoules in this case. Any questions on that there? Yeah. The moles actually cancel out from these numbers in front. So these numbers in front are technically moles, and that's sort of where they cancel out from. Some people will leave it as kilojoules per mole as well, but technically speaking, that's sort of where the moles cancel out from. As we'll talk about in other chapters, which already came before this chapter, since we kind of skip around, those numbers in front are what are considered the moles of each of those things as well. Yeah. And that's why we have to kind of multiply it by those coefficients, because the value we see in the table is how much energy per 1 mole. So obviously if we have 2 moles or 3 moles, that's why we have to multiply it by those numbers. Other questions? This is going to be a exothermic, right, type of reaction, as we do see a negative. So a little exothermic action happening there. Any questions on that there? Yeah. Yeah, so always when you look at a reaction, any chemical reaction, reactants are always on the left-hand side of the arrow, and products are always on the right-hand side. So always when you see any chemical equation written like that with an arrow, left-hand side, always your reactants, which is your starting material, and their products are always on the right-hand side, which is what you're formed. And that's sort of what we were talking about when we talked about state functions as well. We do like kind of our final state, initial state is the important things here. So in a chemical reaction, really our products is our final state, and our reactants is our initial state. So as we do this, we're basically taking final minus our initial state to figure out the energy. Yeah. This is a reaction, RXN. So it's shorthand for reaction. Yeah. Other questions? Okay. I want to try another one here. So I want to try this one, see what you come up with here. A little bigger, maybe. Calculate the delta H, and is it exothermic or endothermic here? Okay, so once again here, we're going to calculate our delta H of the reaction by taking our products. So once again, our products on the right-hand side here. So we're going to look at 16 of the COs. So the value of CO that we find here is negative 110. We're going to add it to our other product, which is 18 of our waters, which is minus 286 here. And essentially, this is going to take care of all of our product side. We're then going to subtract, and I'm just going to go underneath it here. Our reactant side, we have 2 of our first guy there. So 2 times the value from the table there of our first guy, minus 208 kilojoules per mole. And we'll add it to 25 of 0, basically, for our O2 value that we find from the table there. All right, so adding all that together there, 16 times negative 110 plus 18 times negative 286. And we're going to subtract it from basically 2 times negative 208. And not get an error. Let's try that again there. Try that. All right, so it looks like I think negative 6492 kilojoules in this case. Get it? Questions on that one there? Yeah.
Wait, is this calculator? Like, do you put the 16 in the parentheses negative 100 plus the other ones like that, or?
I do. So when I'm doing, say, this here, I actually would, because there's multiple ones I'm going to be doing, I actually will open a parentheses and then open another parentheses and do 16 times the negative 110, close parentheses, then hit add, open another parentheses, 18 times negative 286, close the parentheses, close the next one, which is the big parentheses. That basically will take care of all what we got here on the product side. I would hit equals at that point, and then I would go subtract and open up another parentheses for down here. Kind of do the same thing. Open another one, go 2 times the negative 208. At that point, you really don't have to do this one because it's 0, but you could do it the same way and close parentheses and then hit equals. And then, it should be good. Yep. This obviously is exothermic as well. Again, because of the negative sign here, exothermic overall here, we're going to be releasing energy as a result of this reaction, which does make sense. It's actually a combustion reaction, which typically does release energy. Any questions on how to calculate delta H? If you're just given the reaction, pretty much, if you're just given the equation or the reaction, and you're asked what is the delta H's reaction, that's pretty much what you do. You got to go to that table, look up the values, products minus reactants. It's basically the way you solve for it. Any questions on that there? All right, I think we'll skip that one there. So that's basically what we looked at. All right, so let's talk about specific heat, which is another way that we can look at the energy of a reaction. This is not negative, it's just from PowerPoint, so it's a positive number there on the bottom. Specific heat capacity, which I think we might have touched upon last time as well. Specific heat capacity definition is the amount of energy required to change the temperature of a substance by 1 degree Celsius, 1 gram of a substance by 1 degree Celsius. There is a specific heat equation. I roll with Q is equal to ms delta T. And the different parts of this is Q is heat or energy. And usually that is the units of joules or calories are the kind of 2 units there that you see, joules or calories. S or M here, I'll go up here actually. M is mass, and that is usually units of grams in this equation. S is actually the specific heat capacity, which is this definition we just read there. And that is units of joules per gram per degree Celsius or calories per gram per degree Celsius. That is also the definition of specific heat. Joules is energy. So up on top, the energy to raise 1 gram of a substance by 1 degree Celsius. So that's basically the guy that has free energy. Now, delta T here is the change in temperature. And that is in degrees Celsius. It's probably one of the only chemistry formulas that you'll come across where we actually leave it in Celsius. And we usually leave it in Celsius because the specific heat capacity given to us is typically in Celsius as well. So this is one of the few times we actually can leave it in Celsius. Most of the time we convert things to Kelvin. It's really important when you do the delta T that you do what it says up here. You take the final temperature minus the initial temperature. The reason that is really important is when you look at this equation, S is a positive value, M is a positive value. So the only way for Q to be either positive or negative is actually the temperature value. So it's really important that if you get a negative change in temperature, you keep it because it will give you a negative change in Q. or if you have a positive change in temperature, then it will give you a positive value of Q. So it's really important not just to take the difference in temperature, but to actually do final minus initial, because that's what's going to determine whether or not you're going to get a positive or negative value for Q. Why is that important? Because if you get Q as a positive value, that means it's an endothermic reaction. And if you calculate Q and get a negative value, it is a exothermic reaction. So the value of Q being positive or negative, like we see delta H, tells us whether or not the reaction is endothermic or exothermic. In a lot of cases, you could actually calculate Q using this equation, and if the pressure is the same, it will actually be the delta H for the reaction as well. So you can actually calculate the delta H really simply. You might be wondering, how simple can you do this? Pretty much we'll do it next week. You just need a couple of coffee cups, nice insulators, put some water in there and a lid and a thermometer, and you could basically calculate the enthalpy of a reaction or the heat of a reaction simply by just following the temperature change, for example, what's happening with water. So it's a very simple procedure. A couple of coffee cups, styrofoam cups together, some water, thermometer, and you could pretty much figure out how much energy is being released or absorbed in a reaction. Super simple. Yeah. One is to change in enthalpy, which is if you're just looking at a particular chemical reaction, you just want to know what the overall energy change is. You could calculate based on known values of the table. Q is more something that you typically would calculate experimentally, and basically just like I described there, and we'll do next week, kind of experimentally calculate the value of Q. And in a situation where you do it under constant pressure, which is normal, like if we did in the labs, constant pressure is not really changing all that much. Actually, what you calculate will actually be the delta H value for that particular reaction. So you could actually see how close you would be from what it should be under standard conditions, which is what you find in the table. So those delta H values that we find in the table are under what are referred to as standard conditions, like perfect type conditions, if you will. And that's sort of considered 25 degrees and a pressure of 1 atmosphere. Although a lot of time our pressure is not exactly 1 atmosphere or maybe 25 degrees, when we do it in lab, we would probably do it more using specific heat, more experimentally calculated, but you can relate it exactly basically under constant pressure to the enthalpy as well. Other questions? Okay, so 2 really important numbers that you do need to know is the specific heat of liquid water here, and that is the specific heat of liquid water. And that is the number here. It is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. So those are values that you should know. That is also, if you remember, the conversion between joules and calories, that 4.184 number we talked about earlier. So there's 4.184 joules is equal to 1 calorie. So that's also the conversion as well. So that's definitely something that you should know. I personally use S for specific heat capacity. Some books will use C. Some books will use SH as specific heat capacity in the formula. I personally use S. A lot of books do, but some people use C for specific heat capacity. So if you see it, it's the same thing basically in that case. So here is the specific heat capacity of some different things. And as you can see, it does change with the phase. So this is all water, but solid, liquid, and gas actually has different specific heat capacity. So if you're doing a problem, you're actually dealing with ice and not liquid water, you should not use the 4.184 number. You should use more like 2.03 is actually the number for that. So it does change with sort of the state of it. Once again, that is the number you should know for liquid water, which does pop up a lot. The reason why liquid water pops up a lot is obviously it's water, so it's used, but a lot of solutions, even chemicals that you use, they're water-based. So a lot of times we use, even though it's a chemical, it's water-based. So we use the specific heat of water because that's the majority of what's in that chemical. And that allows us to still do the calculations. So you could actually do these type of calculations if you took like hydrochloric acid, sodium hydroxide, and mix them together. You could actually just use the specific heat capacity of water in that case and figure out the enthalpy change of that reaction to Q just by using the change in the effect of water. As we talked about last time as well, what that means is the higher the specific heat capacity, it's going to take more energy to change 1 gram of that by 1 degree Celsius. So something with a really high specific heat capacity, you would have to put a lot of energy in there to just see the temperature move a little bit. We talked a little bit about that with our bathtub example, right, in our coffee cup, right? So although the bathtub has a lower temperature, it has more thermal energy, but the coffee cup has a higher temperature because it's a much smaller volume, right? So with that much smaller volume of coffee, there's a lot less water in there. It takes a lot less heat to see a bigger temperature change than if you apply the same amount of heat to that big giant bathtub that has all that water in it. You're not going to see as big of a temperature change because there's a lot more grams of water in the bathtub. So again, the larger the specific heat capacity, more energy needed to see that temperature change. We look at temperature change here to figure out, that heat being absorbed or transferred in a reaction. So let's take a look at an example here and see what you come up with. Determine the amount of energy as heat that's required to raise the temperature of 10 grams of aluminum, specific heat capacity 0.89 from 25 to 58. Give your answer both in joules. Okay, so let's take a look and let's just pull out the information. So we're looking for the amount of energy or heat, and that is Q in that equation. So Q is equal to ms delta T. So Q is what we're looking for. We have the mass, which is 10 grams. We have the specific heat capacity, which is S, given to us. If not, you may have to reference like that table we just saw in the previous slide if it's not given to you, which sometimes it may not be in a problem. By the way, this is the one with 3 units, the S. This is the one with only 1 unit, like joules or something like that. So again, they're sometimes very often reversed or confused with each other. We do have a initial temperature of 25 degrees Celsius, and we got a final temperature there of 58 degrees Celsius. So we pretty much got everything on this side. So Q will equal our 10 grams times our S, 0.89 joules per gram per degree Celsius. Again, we want to go final minus initial here. So 58 minus our 25. So again, you want to make sure you always do final minus initial. That will give you a negative sign if you need it, or no negative sign if you do not need it. So 10 times 0.89 times basically 58 minus 25. Going to get us an answer that is 293.7 on my calculator. Grams will cancel. Degrees Celsius will cancel. Going to leave us only joules as our answer. We still need to think about sig figs here. So we got 3 sig figs there. We got 2 sig figs there. When we subtract that, that's like 33, which is 2 sig figs. So we actually should end up with 2 significant figures at this case. Yeah. First off, any questions on? Yeah. Right. That's just joules. I always forget that part of this question. So we do need to do the other part, which is converting from joules to calories. And that is our 1 calorie is 4.184 joules. So if we took our 290 joules, again, a little dimensional analysis, opposites cancel, 4.184 joules on the bottom, calorie up on top, joules will cancel, and we'll end up with I'll use a rounded number since I wrote it that way. You'll end up with about 69.3 or just 69 if we keep it the same there, calories. If you didn't use a rounded number, you'll end up with like 70, I think, calories if you kind of use the 293.7. Exothermic or endothermic, this one? It is endothermic. We got a positive value. We actually see that in our temperature, right? Our temperature started at a lower temperature and ended at a higher temperature. The only way for that to happen is it has to absorb energy, right? So it's got to absorb energy to do that, right? To see a temperature increase. Any questions on that one there? All right, let's take a look at another one here. 294 joules of heat is transferred to 10 grams of silver at 25 degrees. What is the final temperature of the silver if the specific heat capacity is 0.24 joules per gram per degree Celsius? To see what you end up with there. Okay, so let's take a look at it since we're getting to the end here. So obviously we're doing our specific heat. Our Q is equal to ms delta T. In this case, we actually have Q. Remember, Q is the one that has just the one energy unit, which is joules in this case. We do have our mass, which is 10 grams. We have our initial temperature, which is 25 degrees Celsius, and we have our specific heat capacity, which is 0.24 joules per gram per degree Celsius. Again, that is the one that has all three of those units together, the S. We are looking for our final sort of temperature. So we really got all this here. So I'm just going to solve for delta T in this case. So the change in temperature will actually equal Q divided by ms. We're just going to take these guys and divide it to the other side, basically. And putting in our numbers here, we got 294 joules divided by our mass, which is 10 grams, and our specific heat capacity of 0.24 joules per gram per degree Celsius. The joules will cancel, the grams will cancel. That's going to leave us degrees Celsius, which will come up to the top when we divide. Will give us 294 divided by 10, and hit equals divided by 0.24, hit equals. Going to get us 122.5 degrees Celsius. First off, any questions so far on that there? This is not our answer. This is only the change in temperature. So that is not the final temperature, but that is the change in temperature. That is important. The change in temperature, again, is our final minus our initial. That means that our final temperature would equal the change in temperature plus the initial temperature here, basically adding that to the other side, basically. And in this case, I'm actually not going to round at this point in terms of significant figures, so I'm not super far off, perhaps maybe the correct answer. So I'm going to take the 122.5, I'm going to add it to my 25 degrees Celsius, and that's going to get me, I believe, 147.5 degrees Celsius. Now I'm going to think about where I should really end up. So if we go back to our original calculation here, the change in temperature, we got 3 sig figs up on top. We got 3 sig figs up on top, and we got 2 sig figs there on the bottom. That means, technically speaking, this should really be, if we stop the calculation there, about $120 degrees Celsius, right? And that is a whole number added to another whole number, which means really this guy should end up at a whole number and really about 148 degrees Celsius. Now, obviously, if you rounded and used the 120, you would end up at 145, which is about 3 degrees difference. So again, here in this case, I personally would probably hold off rounding until the end, but go back and kind of figure it out. I think I'd probably give it to you if you did round and use the 120 on the back end there. You'd probably be okay. But again, you can see there's a good number of degrees difference if you used a rounded number at this point rather than waiting to the end to do it, bless you, which might be probably closer to the true value of what it should be. Yeah. Because really the last thing that we did here is actually adding. And that takes us now to decimal places, which is why it's important to come back here where we're looking at sig figs, right? And figure out this is technically sig figs what it should be, which is actually a whole number, which tells us when we add it, technically, we would be going to a whole number. Yeah. Other questions? All right, we'll lay it up there.